Hello everyone. In the last two lectures, we talked about the physical and chemical properties of alcohols, and then we moved on to understand the different ways in which the alcohols can be synthesized, especially starting from alkenes and carbonyl compounds as substrates. Then the next we moved on to making diols with the help of dihydroxylation reaction starting with olefins and taking permanganate, KMnO4 and osmium tetroxide as the dihydroxylating reagents. So, with that synthesis and the chemical and physical understanding of alcohols, let us in today's class understand the reactivity pattern, the reactions which are different types of reactions which the alcohols undergo. So, today's lecture will essentially be dealing with the reactions and reactivity of alcohols. That is what we are going to learn today, the reactions of alcohols. But before we start, we should understand what is the kind of reactivity the alcohols have by virtue of the hydroxyl functional group. So, we have a hydroxyl functional group which is sitting next to the alkyl part, and just look at the structure. You have a hydroxy group sitting next to your alkyl, and this imparts some kind of important electronic property to this molecule. So, this hydroxyl group in which oxygen is more electronegative, it pulls the electron density, it is more electronegative than hydrogen as well as from carbon. So, because of this electronic effect, this bears a delta negative charge, and both hydrogen and carbon bear a delta positive charge. So, if we understand this reactivity of this molecule now, we can say that broadly the reactions of alcohols can be classified into two parts, one which involves reactions due to hydroxyl group and the other in which the entire molecule is covered. Okay. So, both the alkyl and the hydroxyl group, that means the entire part of the molecule is covered in giving you the reaction. So, in the hydroxyl group also we can further subclassify it as the reaction in which only the hydrogen atom is replaced. So, reactions involving replacement of hydrogen atom, okay. And the second could be the reactions in which the hydroxyl group is replaced. So, you are replacing the OH group. So, these are the broad classifications of how these reactions can happen. So, if you are replacing the hydrogen atom, that means you are cleaving this OH bond, and as we discussed in the previous lectures, the relative acidity of the alcohols follows the order 1 degree, 2 degree and 3 degree, which tells us that the 1 degree alcohols are the ones in which the hydrogen atom replacement is going to be the fastest. If you replace the hydroxyl group, these are the reactions which you can well understand will be substitution and elimination reactions of alcohol. So, substitution and elimination is what is going to involve a replacement of the hydroxyl group. Okay. So, if we so that is pretty obvious that if you have a methanol, if I am comparing the acidity, or you have a tertiary butanol, right. So, in this case, if I have to compare the acidity of this bond and this bond, you can well understand it by the effect of the 3 methyl groups versus 1 methyl group. So, it is going to change the bond strength of the OH bond and the stability of the complementary conjugate base, which is going to get generated from each of the two alcohols. Next, when we compare the acidity constants of alcohols with other molecules. So, let us see and compare the acidity constants of alcohols with other molecules. Okay. So, let us take the simplest of all, water, and see how they behave with respect to water in terms of their acidity. So, the pKa value of water is known to be 15.74. If I take the simplest alcohol methanol, the pKa value of this molecule is 15.5. I take ethanol, the pKa value of this is 15.9. You take a tertiary butanol, the pKa of this molecule is 18.0, and then you move on to the other classes of compounds like the acetylene and alkyne. You take it in reference with hydrogen, which is 35. You take the nitrogen containing molecule ammonia, which is 38, and then you can compare it with a regular alkane and ethane, which is 50. So, now if you look at the pK value of these molecules, they are increasing, which tells you that the relative acidity is decreasing, which means that the alkane. So, if based on that I have to plot the order of acidity in general for these molecules, I can say water is the most acidic, followed by the general class of compounds alcohols, followed by alkynes, followed by hydrogen, then amines, and then alkanes. So, this is the relative order of acidity of these different classes of compounds. But since we are talking about alcohols in particular, I would like to say that in alcohols, with the exception of methanol, all the other alcohols are weaker acids than water. So, all alcohols except methyl alcohol or methanol are weaker acids than water. So, when we talk about this acidity behavior, we have to understand it in terms of the stability of the conjugate base. So, what is happening in this reaction, that you have an alcohol, okay, and when you are saying that it is acidic, what is happening in this equilibrium reaction? So, this alcohol is giving you, after losing a proton, it is giving you an ion which is a alkoxide ion. Okay. So, you are generating an alkoxide ion, and this is your protonated form of water. This is what is happening essentially when we are saying, when we are talking about the acidity constant of alcohol. So, in this, the acidity depends upon two factors. Generally, it will depend upon the strength of this OH bond, which will again depend upon the nature of the alkyl group, and it also depends upon the stability of the conjugate base. So, we are talking about the conjugate base. Okay. The general norm is that if you have a strong acid, we will have a weak base, that is how it goes. But not only should we have a weak base, we should have a stable base. So, there are two factors when you talk about these alkoxides, okay, and I compare an alkoxide of a sodium methoxide, okay, versus a potassium tertiary butoxide. Suppose I take this, I compare these two bases and I look at the stability of these two bases. Okay. Now, this being a small base, this can easily undergo solvation, right, it can undergo solvation, but this being surrounded by 3 methyl groups is center, this is a bulky base and it undergoes, because of crowding, less solvation, and that is what you were seeing in the trend, that methanol was a stronger acid, right, because it has a weak base. In terms of the order of the basicity of these bases, I can say that the order of basicity will be that sodium methoxide is a weaker base as compared to hydroxide, and then you move on to ethoxide, the same order which we saw for the corresponding acids or the alcohols of these bases. So, the order of basicity for these corresponding conjugates bases arising from these species is going to follow this order, which tells me that this is the strongest base and this is the weakest base. So, we were comparing a tertiary butoxide with a methoxide, and this is a stronger base, okay, and therefore, the corresponding tertiary butanol is a weaker acid. So, these things are based upon two factors, as I pointed out. One, it depends upon the electronic effect of the R group, okay, and second, it depends upon the extent of solvation of the conjugate base, which again will be dependent upon the R group, the steric factor which allows it to undergo extensive hydrogen bonding with the solvent molecules and get stabilized or not. So, with this understanding on the acidity behavior of the alcohols, we now move on to see what are the reactions it is offering as a result of this hydrogen replacement. Okay, so we come to the first class of reactions, which is the reactions replacing hydrogen atom. So, the reactions replacing hydrogen atom, as we just saw, I can conveniently write follows the order 1 degree, 2 degree and then 3 degree alcohols. This is the order of reactivity of the alcohols in terms of the ease with which they are able to replace the hydrogen atom. So, the first reaction in this series would be the reaction with active metals, which we did earlier also in the previous class when we were talking about the acidity behavior of these alcohols. We did it previously with active metals such as sodium, potassium, aluminium. So, these are the reactions in which the alcohol is reacting with the base and it is giving the corresponding alkoxide with the evolution of the hydrogen gas. So, this could be a sodium metal, or in general if I have to write, it could be any of these active metals. You can even have magnesium in these series. So, you can in general say that this reacts with the metal and it gives you the corresponding alkoxide and this gas. So, this is the basis on which we previously also discussed about the formation of the potassium tertiary butoxides and the aluminium tertiary butoxides, which are used as bases in organic synthesis. Okay. The next reaction which talks about the acidity of these alcohols is the reaction with Grignard's reagent. Grignard's reagents, we know, are able to abstract any acidic proton very easily. Okay. So, Grignard's reagent essentially react with active hydrogen species. So, they react with active hydrogen species and the substrate in this case happens to be alcohol. So, when the alcohol reacts with Grignard's reagent, it picks up this hydrogen. Okay. So, this hydrogen is picked up by the alkyl part of the Grignard's reagent and what you get is the corresponding alkane and ROMgX. So, which tells you that this is the stronger acid as compared to this, which is a weaker acid. Okay. The third type of reaction could be when you have the alcohol and you treat it with organic acid. When we say organic acid, it is any carboxylic acid, okay, with organic acids in presence of an acid catalyst. Okay. So, it could be any acid catalyst. We take H2SO4 and if you could remember and recollect, we talked this reaction earlier also when we were talking about the method of preparing the alcohols from esters, and there we said that de-esterification is the pathway. So, you took an alcohol, you took an acid, you reacted the two in the presence of an acid and you formed an ester. The reverse reaction is what is going to furnish you the alcohol back from which the ester was synthesized. So, we are talking right now about the forward reaction in which the alcohol and the acid react to give you ester. Okay. So, you take the acid, this is an acid catalyzed reaction. So, the first step is the protonation. Okay. And this I can conveniently draw its resonating structure in which you see that there is a carbocationic species which is present. Okay. So, the next step, it is again a reversible step and you have attack of the alcohol onto this carbonyl of the acid, and this gives you this is followed by loss of a proton from here, okay, and you get this species. And then there is elimination of water molecule and you are left with this carbon bearing a positive charge, and then this can be reorganized to show in this manner, which eventually undergoes loss of proton to give you the corresponding ester. So, this is the reaction in which the esters are obtained when you treat an alcohol with an acid. So, this is your building block, and this is an acid catalyzed reaction which is giving you an ester. And if you look at this reaction, this involves the replacement of the hydrogen atom of the alcohol. So, that is why we are saying that this is another reaction in which this is replaced and this OR goes and attaches itself to the carbonyl of the acid. Another reaction similar type which furnishes the esters, but with another activated substrate of an acid, is with acid chloride or anhydride. So, this reaction is essentially the same which we just discussed with the acid, but in this case instead of the acid we can take acid chloride or we can take the corresponding anhydride, and both the cases the product which we get is an ester. Okay, so, the reaction is quite straightforward. You take the acid chloride, treat it with the alcohol, and the product is an ester. Okay. Mechanism is essentially the same. Okay, you start with this, you have an activated carbonyl here. So, directly it is attacked by the alcohol OH group, and you get this kind of an intermediate which then undergoes the loss of chloride, because this is what has to quit in order to give you the reaction. So, you get again this intermediate which then undergoes a loss of proton, okay, to give you the corresponding ester. So, this is another reaction in which we are getting esters not from acids in this case, but from acid chloride and or any of its anhydrides. Okay. The next reaction in this series would be with the corresponding phosphoric acid. So far we have talked about the carboxylic acid. We can also have phosphoric acid giving you similar kind of esters, which in this case will be phosphates. So, we see that when we have the alcohol treat with phosphoric acid, just the way we treated with carboxylic acid, we got the corresponding carboxylate ester. In this case, when you treat it with phosphoric acid, what do you get? So, the alcohol is treated with H3PO4. This is the structure of phosphoric acid. As you can imagine, in case of carboxylic acid, there was one OH group, right, attached next to the carbonyl. In this case, you have 3 hydroxyls which are attached next to the P double bond O. So, we expect, or we do not know if each of these are going to get replaced. So, the first thing which happens is elimination of a water molecule, and you get the corresponding product in which one of the OHs is replaced by OR, and this is called alkyl dihydrogen phosphate. Okay. So, you have alkyl dihydrogen phosphate, this is what you get, but the reaction does not stop here. It can react with another molecule of alcohol with the elimination of water. It can give you the next product, which is going to be the second hydroxyl substituted by OH by OR, and what you get is this product, which is dialkyl hydrogen phosphate. Okay. So, this is what you get now, and since there is one more OH available, it can react with one more molecule of alcohol to give you eventually the all phosphorylated product, which is a trialkyl phosphate. So, what you get in this case is a trialkyl phosphate, and we know that these phosphates esters of phosphoric acids are important in biochemical reactions. So, when you look at this phosphate, what comes to our mind is ATP, right, which is adenosine triphosphate. So, these esters of phosphoric acids, these are important when we talk about the biochemical reactions. So, this is another instance where you can see that your OH is cleaved and OR is what is attaching to the phosphorus unit to give you mono, di and trialkyl phosphates. Okay. Going ahead in this series, the next reaction is very interesting and it has a very important use also. This is a reaction in which the hydroxyl group is converted into a good leaving group. Okay. So, your hydroxyl is converted into a good leaving group. What do I mean by that? So, what is happening in this reaction is that the alcohol is treated with, so this is a reaction with alkane or arene sulfonyl chloride. Okay. So, just now you were treating with the phosphorus based reagent and now you are treating with the sulfur based reagent, which is a alkane or arene sulfonyl chloride, given by the general formula we can say can be RSO2Cl or ArSO2Cl. So, the interesting thing here is that this alkane sulfonyl chloride, this could be a methane sulfonyl chloride. Okay. So, this could be a methane sulfonyl chloride, and when you treat an alcohol with a methane sulfonyl chloride, you get the corresponding sulfonates which we call as mesylates. So, these mesylates are nothing but these are methane sulfonate esters. Okay. You get methane sulfonate esters. So, what is a general reaction? We will talk about that, but before that, if you treat it with, if your AR happens to be para-toluene sulfonyl chloride, okay, we say para-toluene sulfonyl chloride, you treat it with this, the corresponding compounds which we get are called tosylates. Okay. In this class methane sulfonyl, you can also treat it with trifluoromethane sulfonyl. Okay. So, you can treat it with trifluoromethane sulfonyl chloride, and in this case the compound which you get is a trifluoromethane sulfonate ester, which we call as the triflates. So, all these are important compounds because they are good leaving groups and they are widely used in synthetic organic chemistry when a hydroxyl is transformed into these tosylates, mesylates, right, triflates, and then it is used for subsequent functionalization. So, the reaction I am going to write here involves the reaction of your alcohol, general reaction. You treat it with any alkane or arene sulfonyl chloride in the presence of pyridine as a base, and what you get is the corresponding sulfonate ester with the elimination of HCl. So, now you can well rationalize the reason for adding pyridine, that it is used to take away this HCl which is generated during the reaction and form this pyridine HCl salt. Okay. So, this is basically to neutralize the HCl. So, the mechanism which goes into this reaction is the following. You take the alcohol, treat it with the sulfonyl chloride. So, the reactivity of these sulfonyl bonds you can well visualize will be both ways. You can have, this is the kind of reactivity it is going to have, but let us show with one of these oxygens. So, this is going to be attacked by the alcohol, right. So, in the presence of pyridine your reaction is happening. So, what you get is this intermediate. Okay. So, you get this intermediate which is unstable and immediately undergoes loss of chloride ion to give you now this proton, which is already acidic, is picked up by the base, okay, and what you get is your corresponding sulfonate. Okay. So, this is a sulfonate which you get when you treat an alcohol with the sulfonyl chloride. You are getting the sulfonate esters which are good leaving group, and because they are good leaving group, they are widely used in the substitution reactions in which you have a nucleophile and you have converted an alcohol into its sulfonate, and this eases the substitution reaction to give you the corresponding substituted product with the release of the sulfonate, because it is a weak base, okay, the sulfonates, and it is a very good leaving group. That is why the alcohols are generally converted into these sulfonates for substitution reactions. The next set of reactions is the reactions replacing OH group. So far what we did was the reactions in which the hydrogen atom was replaced. Now we are going to talk about the reactions in which the entire OH is replaced, and in this I told you essentially we have the substitutions and the elimination reactions. So again there can be very many ways in which the OH group can be replaced. The most important one is with halogen acids. So we talk about halogen acids. So what do you mean by halogen acid? It is represented by the general formula HX, where X is your halogen. Your X could be iodide, bromide or chloride. Okay. So your halogen acids can be either a dry HX gas, which means you can have either dry HI, HBr, HCl, or you can also use concentrated aqueous forms of these acids. Okay. So we can have concentrated aqueous acid. Either of these forms, the reactivity of the halogen acid follows this order, that the iodo is the most reactive, followed by the bromo, followed by the chloro, and that is what imparts difference in the conditions under which each of these substitutions with the acids can be carried out. For example, if we use HI, we generally keep the temperature below 100 degree centigrade. So it is a much milder substitution. If you keep HBr, you can use either concentrated HBr, or you can also have in situ generation of HBr by using a salt like a potassium bromide or sodium bromide and treat it with concentrated sulfuric acid. So when we reflux it, these are the conditions when we use HBr as the reagent. If we use HCl, HCl is a weaker, chloride is a weaker nucleophile, okay, and it will not react the way the iodides and bromide does, okay, because it is a weaker nucleophile. So for using HCl, we use concentrated HCl along with anhydrous zinc chloride, which we know behaves like a Lewis acid. You must have come across these in the Friedel-Crafts reaction. So we add zinc chloride which act as a Lewis acid, and we carried this reaction out under heating. So these are the different conditions in which each of these halogen acids has to be used depending upon the difference in the reactivity pattern of these acids. Okay. So the reaction is a substitution reaction, you would have guessed by this time, it is a substitution reaction, okay. And since we are using an acid, this reaction is also an acid catalyzed reaction, okay. Reaction with halogen acids is an acid catalyzed reaction. So what is the need of an acid? You are working with an alcohol, you treat it with HX, you are getting the corresponding halide with the elimination of a water molecule. But we say it is an acid catalyzed reaction. The reason for using an acid here is that the acid protonates the alcohol, okay. It protonates the OH of the alcohol and makes it a good leaving group. So this is probably the same thing which talked a few minutes ago, that to convert it into a good leaving group, you are converting into the corresponding sulfonates, because OH itself is not a good leaving group. So it is an acid catalyzed reaction which protonates it and makes OH a good leaving group and facilitates the substitution. Okay. So what is happening with the different kinds of hydrogen halides. So, if you have the alcohol, okay, and you treat it with, let us say, the HBr, okay, it is a simple substitution reaction. You get the corresponding bromide, and this is about it. If you use the corresponding chloride, we are saying that this is not working for this one, and the ease with which a bromine is able to replace a hydroxyl is not the same with which a chloride can do so, and there is no reaction if you just use a concentrated HCl for carrying out the substitution. So, in this case an additive is added, which is your zinc chloride, I just said behaves as a Lewis acid, and what does it do is it activates your hydroxyl by coordinating here, and you form this kind of an intermediate, which is then quite active. So, your oxygen is bearing a positive charge, okay, and then your halide, which is a chloride in this case, which comes from HCl, okay, this is now able, when it attacks this, it is able to form the corresponding alkyl halide easily because of this bond polarity induced with the help of the zinc chloride salt, and then you get ZnOH Cl2. This is formed along with, or you can also represent it like OH Zn Cl2, which then undergoes, in the presence of the acid, it forms ZnCl2 with the elimination of water. So, this is added as a Lewis acid, and this reaction you would have also come across. It is a test for confirming what is the type of alcohol. If you are able to guess this, your zinc chloride and HCl, it is also known as the Lucas reagent. Okay. You might have come across this reagent name, and this is a reagent which is used for distinguishing between the primary, secondary and tertiary alcohols. So, what it does is when you add this Lucas reagent to a 1 degree alcohol, it gives no turbidity. This is the visual interpretation that there is no turbidity. Okay. If you add it to a 2 degree alcohol, we say the turbidity appears in 5 minutes, and if you add it to 3 degree alcohol, we say the turbidity appears immediately. So, the question is, what is this turbidity due to? This is what the reaction is. We have shown you that the chloride is replacing hydroxyl, you are forming alkyl halide, and this reaction is carried out under aqueous condition. So, when you have this alkyl halide formation, this is what it imparts turbidity to the reaction to your solution because of its insolubility in the aqueous media. So, when you have a 3 degree alkyl halide, immediately it gives you turbidity because of the formation of the 3 degree alkyl chloride. Okay. Let us see a few examples with which these halogen acids are able to substitute. I will take a few examples. You take N-pentyl alcohol. So, you start with N-pentyl alcohol, which is a 1 degree alcohol. You treat it with HCl, and you have to add anhydrous zinc chloride and heat it, because otherwise the reaction will not go, and then under these strong conditions what you get is the corresponding N-pentyl chloride. This is how these alcohols react with the halogen acids to give you the corresponding alkyl halides. If you start with the 2 degree alcohol, let us say you start with isopropyl alcohol. You treat it with concentrated HBr, or the other bromide source could be NaBr with H2SO4. Under reflux conditions, as we just discussed, you get the corresponding bromide. Okay. If you take a 3 degree alcohol, tertiary butanol, for this you need much milder conditions. Okay. You treat it with concentrated HCl, even at room temperature, this gives you a tertiary butyl chloride, and this we saw is based upon the reactivity of 3 degree alcohols is much more as compared to 2 degree as compared to 1 degree. This is what we just saw. So, the second method now will come across a second method which is used for this kind of substitution, and this is when we treat the alcohols with phosphorus halides. Just now we saw that alcohols react with phosphoric acid to give phosphates. Now, we are going to talk about another phosphorus based reagent which are phosphorus halides, which could either be PCl3 or PCl5, PBr3, which is phosphorus with bromine, it could be phosphorus and iodine. All these reactions, when we treat the alcohol with this, we get the corresponding alkyl halides. So, these are the phosphorus reagents which are used for conversion of an alcohol substitution with the halide. So, you treat alcohol with, let us say, PCl5, the products which you get is an alkyl halide, alkyl chloride in this case, and POCl3 along with elimination of HCl. So, this is a general reaction which goes, but what is the mechanism? How are these formed and what is the kind of pathway this reaction is adopting? So, you have ROH and you have PCl5. Okay. So, if you have 5 chlorines attached to phosphorus PCl5, the first step is loss of one of the chlorides here, okay, and what you get as a result is this intermediate. You get this intermediate, and this is followed by loss of H plus and Cl minus. That means, there is a loss of HCl here, and what you get is this intermediate, okay, which eventually, so in the presence of the chloride ion, okay, the chloride ion comes and picks it up here, and what you get is this product, which is your alcohol substituted with the chlorine. Okay. So, in this reaction, alcohol can also react with phosphorus in bromine, PBr3 is the reagent. It gives you alkyl bromide along with formation of H3PO3. Okay. And if we balance this, so it will be 3 molecules of alcohol giving you 3 molecules of alkyl halide. And the mechanism for this reaction can be rationalized like this. You have alcohol reacting with PBr3, the trigonal structure. So, the first instance is the removal of the Br minus to form this intermediate. Okay, so, this is kind of a SN2 type of displacement in this case, that the Br minus leaves, this comes, and then this is a protonated, essentially this is a protonated alkyl dibromophosphite. Okay, this is a protonated alkyl dibromophosphite, and this then in the presence of Br minus, essentially the same thing is happening as was in the previous case. This goes and attacks here. So, what you get is RBr plus this, and which can again, since there are 2 bromines present here, it can again react with 2 molecules of alcohol, right, and undergo loss of these 2 Brs to give you 2 molecules of alkyl bromide along with formation of this acid, which we can say is a phosphorus acid. Okay, I will give you few examples how these alcohols react with PBr3 and what are the other implications involved. So, when you treat it with PBr3, this is a primary alcohol, Okay. This is 2 methyl 1 butanol. So, obviously, it is a 1 degree alcohol, we expect it to undergo SN2 type of reaction, and what you get is the corresponding 2 methyl 1 bromobutane. If you start with a 2 degree alcohol, which is 1 phenyl ethanol, under the same conditions, bromination with PBr3, you will end up getting the complementary brominated product, which is 1 bromo 1 phenyl ethane, and since these are going by SN2 pathway, okay, so 1 degree or 2 degree alcohols easily undergo this bromination, and in this there is no carbocation formation. Obviously, if it is going by SN2 pathway, there is no carbocation formation, there is no rearrangement, unlike as was witnessed in the case with halogen acids, that there was the carbocation forming was undergoing a rearrangement. Since there is no carbocation, there is no rearrangement, especially when you carry out this reaction at or under 0 degree centigrade, and therefore, we say that PBr3 is the preferred reagent for alkyl bromide formation. Okay, so, for these reasons, this is the reagent of choice when we have to carry out or make the bromides from the alcohols. All right. So, this was about the alkylation with halogen acids and with phosphorus reagents. Let us look at another reagent for carrying out the halogenation of alcohols, which we call as a thionyl chloride. Okay. So, with thionyl chlorides and the reaction with alcohols is very interesting again, because in this case it is a very clean reaction. Okay. You start with the alcohol, treat it with thionyl chloride in the presence of pyridine, you get the corresponding alkyl halide with the evolution of sulfur dioxide and HCl, both of which are gases. Okay. So, we say it is a very clean reaction and specially suitable for formation of alkyl chlorides, which otherwise if you use a halogen acids require much harsher reaction conditions. Okay. So, you can have a primary alcohol, you treat it with SOCl2 in pyridine, you get the corresponding halogenated compound. Okay. So, it is an important reaction for synthesizing the chloroalkanes, and the mechanism which goes into this reaction can be interpreted like this. You have a sulfonyl chloride SOCl2. So, based upon the reactivity pattern, obviously we expect that this bond is polarized, and this is what is going to be the first line of attack, and what we get from here is this intermediate. Okay, which instantaneously undergoes loss of this Cl minus to give you the corresponding intermediate. And now, since we have pyridine in the reaction medium, it picks up this acidic proton and we get the alkyl chlorosulphite, okay, along with formation of this pyridinium salt, and then eventually the last step is that your alkyl chlorosulphite which is formed, okay, in the presence of pyridine, undergoes this reaction when you get the alkyl halide along with formation of this intermediate, which eventually results in loss of sulfur dioxide along with the regeneration of pyridine. So, this is the overall mechanism of the reaction, in which you can see that sulfur is eliminated as the SO2 gas. So, this is a good method for the synthesis of the alkyl chlorides. Okay, so now we move on to the third type of reaction, in which we have reactions involving both the alkyl and the OH groups. Okay. So far what we have studied is, if it is only the OH bond breaking, hydrogen is getting substituted, or the entire OH functionality is getting substituted. Now we will deal with reactions, the third type, in which both the alkyl and the OH groups are involved. And in this we have three types of reactions. One is an oxidation reaction, which involves both parts. Another type of reaction is a dehydrogenation reaction, and the third part on this is a dehydration reaction. So, these are the three types of reactions in which both the alkyl as well as the OH groups are involved, and we will take up each of them one by one. Let us talk about first of all the oxidation reaction, oxidation of alcohols. So, oxidation of alcohols looks to be a very trivial reaction, but it is a very interesting reaction, because there are a number of oxidizing agents which are available today for carrying out the oxidation of alcohols to different species. Okay. So, a number of different oxidizing agents are available. So, we can have alcohols, again depending upon the fact they are primary, secondary or tertiary. They have different ease with which they can get oxidized, they can different products which can be obtained as a result of their oxidation, and the kind of oxidizing agent which is used to carry out this kind of transformation. What we are going to discuss today are the reagents based on manganese 7 and chromium 6 species. Okay. So, number of oxidizing, I mean if I go on and telling you about the type of oxidizing agents available, it can be a one full course in itself, but we will restrict ourselves to manganese 7 and chromium 6, the traditional and the most well studied oxidizing agents for oxidation of alcohols. For manganese 7, the reagent which we use is KMnO4, potassium permanganate. It can be used under acidic conditions. So, we have acidified KMnO4, or it can be used under alkaline conditions, in which we have alkaline KMnO4. Both these reagents are able to carry out the oxidation of 1 degree alcohols directly till the acid. Okay. So, if you take a 1 degree alcohol, let us say you take this alcohol and you treat it with KMnO4, it is going to oxidize it all the way till the end, till you get the corresponding acid. If you treat it, this alcohol with KMnO4, the corresponding acid which you will get is this. So, you can see that if you started with 1, 2, 3, 4, 5 carbon system, you ended up with 1, 2, 3, 4, 5 carbon system in the acid. That means there is no loss of carbon atoms when you are carrying out the oxidation of an alcohol till the acid. And another important feature of the KMnO4 oxidation is the change in the color, which is also used as a test to see if the oxidizable functionality is present in the molecule. So, you treat it with basic aqueous KMnO4 solution, okay, which means you have KMnO4. Basic means you have under alkaline you put some hydroxide, it is aqueous, and you heat it, you get the corresponding potassium salt of the acid first, which then gives you the corresponding acid along with the formation of a brown precipitate of MnO2. So, you started with the basic aqueous KMnO4 solution which was purple in color, and you ended up with a brown PPT. That means this reaction is taking place and there is an oxidizable functionality which is changing the color of manganese from purple to brown. The other important reagent in this series, as I said, is a chromium 6 reagent, and a chromium 6 reagent again can be used in different ways. The most popular and important ones are, we used chromium trioxide in dilute H2SO4, and this mixture is taken in aqueous acetone. Okay. This reagent, when you take in dilute H2SO4 chromium trioxide, it generates what we call as the chromic acid. So, it gives you chromic acid which is H2CrO4, and this reagent is known as the Jones reagent. It is the popular Jones reagent which is used for the oxidation of alcohols. Okay, you can, so one, you can use the chromium trioxide, or you can directly use the chromic acid or sodium chromate in H2SO4 water mixture, which again can carry out the oxidation of any alcohol or 1 degree or 2 degree into the corresponding aldehyde or ketone. So, what is so interesting about this Jones reagent or the chromium based reagents is that if you start with the alcohol and you treat it with the chromium reagent, which is orange red in color, you get first of all the corresponding aldehyde if it is a 1 degree alcohol. You stop at the aldehyde stage along with the formation of chromium 3 plus ions which are green in color. But the reaction is difficult to stop at this point, and it further in the presence of the available chromate ions gets converted into the corresponding acid. But what is visually appealing here is that the orange red color of your solution changes into light green because of the presence of these chromium ions. So, when you have a KMnO4 solution, your purple color changes to brown, but if you have a dichromate, your orange color changes to green, and these are the visual indications that an alcohol functionality is present in the molecule. So, let us now look at the mechanism of this oxidation with chromic acid, and more importantly that if you have a 1 degree alcohol, right, it first reaches up to the aldehyde stage and then it goes finally up to the acid when you treat it with the chromium based reagent for carrying out the oxidation. So, let us see the mechanism, how it works. So, you start with the alcohol, I am taking a 1 degree alcohol, you treat it with chromic acid. Okay. The first step is the loss of this water molecule to give you a very important but unstable intermediate. So, chromium here is in the oxidation state 6, right, and here also it is in the oxidation state 6. You get this intermediate which is a chromate ester. You get this chromate ester which is unstable, it cannot be isolated. Okay. So, the next step is immediately that since you are working under aqueous conditions, the water molecule you get the corresponding oxidized alcohol. This is the oxidized form of the alcohol, along with formation of this reduced chromium species. Okay. So, you have a reduced chromium species which can be written as HCrO3 minus, and the oxidation state of chromium here is 4. So, we have oxidation of alcohol to aldehyde, and we have chromium 6 getting reduced to chromium 4 species, which eventually through complex disproportionation and oxidation reactions, it forms a chromium 3 species, the mechanism of which I am not going to discuss here today, but you have to understand that this green color is because of the formation of the chromium 3 species, which is getting generated from HCrO3 minus, which is getting generated during the reaction. It gets, again it can get protonated here, HCrO3 minus. You are working under acid conditions to give you this molecule, which is H2Cr O3. So, now the point is that the reaction does not stop here, and let me also talk about the change in the oxidation states which is happening. So, you started with the alcohol in which the formal charge on carbon was -1. Okay. When you oxidized it till the aldehyde stage, the formal charge on carbon now becomes +1. So, this tells you that this is an oxidation reaction of alcohol to aldehyde. The -1 is changing to +1. So, you are gaining 2 here. So, you are losing 2 here. So, this is an oxidation, and your chromium 6 is changing to chromium 4, and it is a reduction process with the gain of 2 electrons. We move on now to see that what happens, that this reaction does not stop at the aldehyde stage, and it further continues on all the way to give you the acid. So, you have now the aldehyde with you. Okay. Under aqueous conditions, what is happening? This is delta plus, delta negative. You get this intermediate, and you can also write this, rewrite this as this intermediate, which is an unstable aldehyde dihydrate. Okay. So, it is an aldehyde dihydrate which is formed when the aldehyde is there under acidic aqueous conditions. So, once the aldehyde forms a dihydrate, next series of steps is the same as were for the oxidation of the primary alcohol, as we just saw that there is loss of a water molecule, there is formation of this chromate ester, okay, the same sequence of reactions, and then eventually this is lost as in the presence of water, this is lost as an acid along with formation of this chromium species, which can further take up the proton to give you H2Cr O3.